Good morning, everyone, for today's distinguished webinar series in AI and cybersecurity. Today's title of the talk is Securing the Modern Power Grid, Challenges in the 3D Energy Transition. Today's speaker is Dr. Harris Constantinou, Associate Professor, Electrical and Computer Engineering and from King Abdullah University of Science and Technology. Dr. Harris is an associate professor at KAUST, Saudi Arabia. He received the MEng degree in the ECE from National Technical University of Athens, Greece, and the PhD degree in electrical engineering from New York University. Before joining KAUST, he was an assistant professor with the Center for Advanced Power Systems, Florida State University. His research interests include critical infrastructure security and resilience with special focus on smart grid technologies, renewable energy integration, and real-time simulation. He is a senior member of IEEE and currently serves as an associate editor for IEEE Transactions on Smart Grid and IEEE Transactions on Power Systems. Thank you so much, Dr. Harris, this morning for being here at UND. We appreciate for taking the time to do this webinar for us. It means a lot to us, and the floor is yours.
Thank you so much. There is an automatic timer for for the light in the office, so it turned off. Sorry for going away. Let me go back and share my screen again. Let me make sure that everything is visible. Okay, I guess you can see the full presentation.
Yes, we can. Yes.
Okay, perfect. Thank you so much again for the introduction. It's a pleasure to give this talk. At any point, feel free to interrupt me and ask any questions or post any questions in the chat. And of course, after the talk, we can chat with anybody that has any, queries about the presentation. So, as mentioned, the title of the presentation is Securing the Modern Power Grid. And I will discuss a little bit about the work that we do here in my group and essentially what I think and what I see as the challenges in what we, in the community called the 3D era or the 3D kind of energy transition that is happening in power systems. Before doing that, just to give a small background where I am currently in the past 5 years. So a lot of people maybe are not aware. KAUST is it's an international graduate-only university in Saudi Arabia on the shores of the Red Sea on the west coast of Saudi Arabia, an hour drive from Jeddah, which is the second largest city in Saudi Arabia. It's a relatively new university. It was established in 2009. And as I mentioned, we have only graduate degrees. We don't have undergraduate degrees. And an interesting thing about the university here is that we are a small city, right? Whoever works in the university lives in the university. So it's a really nice community that you can really focus and be quite productive in order to push the boundaries in terms of research. It's a relatively small university, as you can see from quick numbers here. We have around, as of last year, around 1,700 students. Most of the students are international, and most of those students also are PhD students. A relatively small number of faculty that gives the opportunity to interact, in classes and in terms of research with students, more efficiently. And it's really international. We have people from all over the world, more than 100 nationalities in the campus, which is a quite big campus, 39 million plus square meters. So, giving this background, moving a little bit towards the research perspective and introducing a little bit the theme of the talk, just as a gentle introduction, what we do in my group is we try to bridge the gap and the level of understanding of what we call cyber physical energy systems, and at the same time focusing on cybersecurity, resilience, reliability, and the control of those systems. So what we do in my group, we try to build models and algorithms to evaluate those developments in realistic testbed setups that we aim to simulate the dynamics from both worlds, the cyber domain and the physical domain, in what we call real-time co-simulation testbed setups. So for those that are not aware, traditionally power comes from large generation plants that generate power from typically fossil fuels such as carbon or natural gas. And this power is transferred through long transmission lines that connect to several distribution substations that distribute this power to cities and customers. And this hierarchical kind of structure of power systems with centralized control themes or features has been the operating principle of the power grids in the last century or even more. However, in the last couple of years, things started to change in what we call the 3D era of power systems, right? With many efforts towards decarbonization, with many climate change initiatives and a lot of renewable energy resources integration into the system, decentralization with a shift to prosumers and microgrids, and of course digitization with AI being the core of the digitization efforts, not only in the energy industry but many other kind of applications and sectors, communications, automation, and electrification. Specifically in the decarbonization kind of aspect, we have seen that in the last couple of years, what we call conventional or centralized power plants based on fossil fuels are slowly going away. For example, coal-based power plants are closing all around the globe. UK announced that it will shut down all coal power plants by the end of last year. And China is close or cancel 103 in 2019. And at the same time, what we have seen in those charts here is the fact that the first of all, the installation of RES, of renewable energy resources, especially PV, is growing very fast. Here in the Kingdom of Saudi Arabia, the goal is to achieve 50% of total generation capacity from renewables by 2050. And also at the same time, the cost of those technologies is increasingly coming down. For example, newly installed renewable power capacity costs less than the cheapest option based on fossil fuels, right? And as we can see in the last kind of 10, 15 years, lithium-ion batteries and solar PV have come down in terms of technology cost by 85 and 82% respectively. In addition to the decarbonization, decentralization also plays an important role. Centralized power plants, again, are going away. Instead, we have what we call distributed energy resources that are being installed near where they will be used, and they're increasing in a very fast-paced. And in addition to that, another important aspect of this transformation is not only how generation is changing in terms of resources used and decentralization, but also how load profiles, how do we consume electricity is changing. For example, electric vehicles increase, the sales of electric vehicles increase faster than any other type of vehicle sale. About 6% per year. And as you can see from this quote here, for example, in Saudi, the goal is by 2030, at least 30% of the vehicles in Riyadh, which is the capital here, are expected to be electric. And lastly, in this 3D era, in this 3D energy transition, the digitization of power systems that started a couple of decades ago is still in progress, right? Initially, we started with advancements in information and communication technologies in SCADA systems, supervisory control and data acquisition systems. But also recently, we have seen a lot of changes at the edge, as we call, of the grid operation, on the metering infrastructure, with the integration of smart inverters, appliances, demand response programs, etc., etc. And this is particularly interesting, especially here in Saudi, because there is a special focus on critical infrastructure. As you can see, the weight of energy, of ICT, of information and communication technology spending in terms of sector, the highest is on the energy sector, and because of the importance of this sector to the operations and to the country itself. So talking about the decarbonization, decentralization, and digitization, one thing that we have to keep in mind is that yes, there are benefits from distributed and grid energy. However, we still have issues that need to be resolved, right? For example, in 2016 and 2019 in South Australia and UK, we have witnessed blackouts because grid operators fail to comply with their performance requirements and with the standard requirements of their generators in order to ride through certain disturbances after some extreme weather conditions that led to damage of the transmission lines. And those events, although not related to cybersecurity, essentially highlighted the importance of properly modeling and controlling renewables to respond in a robust, in a proper way to abnormal events. Also, another thing that is important is that historically, what we call independent system operators directed those conventional resources, those controllable power plants, to move up and down in terms of their generation output based on the instantaneous or variable demand, right? But with the growing penetration of renewables, there are higher levels of what we call non-controllable variable generation resources. And because of that, ISOs, independent system operators, need to direct controllable resources to match not only the variable demand, but also the variable supply. So what you see here on this graph, if you can see my laser pointer, is what we call the duck curve, right? This is a phenomenon that has become increasingly problematic in the recent years because we have so much solar that came online that has been connected to the grid. And the problem with so much solar is that it generates most of the electricity during midday, during noon, during when the sun is most intense. But this doesn't align very well with our daily use patterns because people come from work at home in the late afternoons. They turn on lights, air conditioning, appliances. So this leads to cheap renewable energy and glut of cheap renewable energy during midday, and an extra strain in the system during the evenings, right? And recently, this dark curve is getting deeper and deeper. And recently, a presentation from the EPRI president showed this, canyon curve that has now emerged because, the net load, essentially the load minus the net demand, and demand minus wind and solar has gone negative. And that means that we have to switch off resources that cannot get on quickly over this canyon during sunset. Otherwise, we have to curtail, solar or wind and wasting zero cost clean energy. So just to summarize, right, to ensure supply and demand match at all times, we need controllable resources that have the flexibility to change their output levels and start and stop as dictated by the real-time grid conditions. So in addition to those integration issues, we have, of course, operation interruptions due to information and communication technologies, as evident by the numerous incidents in the past 20 plus years, right? And I'm sure many people and most of you are aware with Stuxnet, one of the first and most sophisticated malware that was uncovered in 2010 and thought to have been in development since 2003, knowing for targeting and disrupting nuclear power plant facilities. And the important thing about Stuxnet is it marked a significant shift in what we call cyber warfare because it was the first and demonstrated the potential of digital attacks to cause physical damage to critical infrastructure. And since then, we have seen numerous incidents. For example, a couple of years ago, in Utah in March 2019. There was a cyber attack that disrupted a renewable utility because an authenticated attacker used known firmware vulnerabilities that caused periodic blind spots for the grid operators for more than 10, 12 hours. Essentially, this didn't cause any blackout, but essentially made the operator lose contact with those parts of the grid for more than 10 hours, essentially not being able to understand what is going on in the system during that time. So the big question, considering all these changes, right, that we try to answer, at least as part of our research, in simple terms, is how to keep our lights on while ensuring pretty much system security, system reliability, despite all those kind of adverse conditions. So in order to do that, in my group, right, and considering those 3D challenges that I mentioned before, we want to assess an impact and understand the impact of those events on cyber physical energy systems, detect potential attacks, excuse me, in inverter or renewable rich grids, and then ensure pretty much optimal operation of the system despite those disrupting conditions. So in the next couple of slides, I will try to highlight some of the work that we do in each one of those themes. So the first direction that we work, as I mentioned, is the area of assessment and understanding the impact of disruptive attacks on cyber physical energy systems. The idea here is to understand how attacks on grid edge devices can escalate from the edge and propagate to global effects, affecting the broader distribution and transmission systems. And this is quite important because it highlights the interconnected nature of energy infrastructure and the potential, if I say that localized attacks, can potentially have widespread impacts. So the contributions that we have done in this area is, first of all, identify critical points in the network of the grid from which an attacker can launch the most effective attacks with minimal efforts, or what we call load altering attacks that we'll explain in a little bit. And additionally, performing temporal analysis, essentially examining how the fluctuations of the loads and the variability of the renewable energy can influence the impact on the system. To provide brief background, right, in our electric grids, various generators operate together, right? They rotate in sync in order to satisfy the electricity demand. So in a stable grid, generation matches the load, and we maintain what we call the nominal frequency of 60 hertz, right? So in abnormal conditions, this balance can be disrupted, right? For example, if generation exceeds the load, the frequency rises, and if the load exceeds generation, the frequency falls. However, it's important to note that not all generation resources contribute equally to this system balancing, right? So renewable sources like solar and wind, despite all the benefits that we all know, they provide what we call little inertia compared to traditional generators. This is because they don't have large rotating masses. And just to understand, the higher the inertia, the more resistant is the system to frequency changes. So a system with high penetration of renewables with lower inertia will experience a faster and potentially more significant drop in the frequency in response to a power mismatch. So while keeping this in mind, right, and considering this principle of grid operation, it's very important to note that utilities do careful planning and management with the forecasting teams to predicting the demand for the next day, for the next month, for the next years, and help the control engineers prepare so they can draw on electricity generation quickly to meet the sudden changes in demand. So what we see here on the on the left-hand side is what we call the TV pickup effect. So in a European Championship in 2021, right, England was playing with Germany, and most of the English people were watching the game in their TV, right? So a lot of people glue to the TV. So the national control room in the UK saw around 1 gigawatt of electricity demand pickup during halftime, because a lot of people turn on their kettles in order to prepare their tea, their coffee, etc. And then, around 2 gigawatts of, in decreased in load until full time, right, of the game. So in our work, we have studied and analyzed essentially how those load changes, right, can be potentially exploited by attackers in what we call, as I mentioned before, load altering attacks. So the idea of load altering attacks is that an adversary can trigger an unexpected or a sudden demand increase or decrease of what we call IoT connected high-wattage appliances, or even DRs, or even distributed energy resources, with the objective of causing grid instabilities. So the main idea is that the frequency fluctuations from such load altering attacks, from such adverse events, by be able to control a large amount of load, in sync over a control area by the attacker, can lead to exceeding nominal frequency limits and potentially, causing load shedding incidents or equipment failures to the system, right? And load altering attacks are becoming a real threat because the number of controllable or IoT controllable DRs and loads is increasing exponentially. So by disrupting the system's normal operation, we can cause some degradation or potentially render it unavailable, unstable, because of disrupting this generation demand balance. However, an attacker doing that, is not so straightforward. He needs to be aware that electric power systems have what we call protection and control mechanisms to maintain the frequency within nominal ranges, within nominal limits. And he needs to be aware of those protection devices in order to, activate certain mechanisms to achieve his or her purpose, right? For example, as you can see on this graph on the top right figure, and during, if the frequency deviates more than 0.04 hertz, right, governors are employed to account for those discrepancies and stabilize the system. And during more severe incidents, for example, above 62.2 hertz or below 57.8, right, you have switching equipment and relays that will trip to protect the generators from potentially catastrophic fluctuations. So in one of our initial works in this area, what we have done, essentially we examine the dynamic impact of frequency stabilities that can be potentially caused by load altering attacks. So the idea was to identify load patterns that can cause abnormal loading conditions and essentially create some vulnerable circumstances that attackers can use in their advantage to perform LLAs, load altering attacks. And essentially, during this first study, we were able to identify, most affected regions, for example, in the US, using public data, and observe how low net load conditions, for example, that happened during the pandemic a couple of years ago, could make scenarios and locations more vulnerable to load altering attacks compared to some other times. However, one important, parameter of doing this analysis is that, there is a simulation kind of challenge, because you have to model, coordinated and synchronous load demand attacks at different locations, right? and you have to model diverse load profiles across the system. So in order to alleviate those simulation challenges, and I will quickly skip the theoretical part or the mathematical part, we have built a theoretical framework to assess how low inertia conditions, because of the high penetration of renewables, can adversarially affect the system resilience to load altering attacks. So the main idea here was how we can theoretically quantify the magnitude in a power grid of load altering attacks that can cause unsafe frequency deviations. So what we derive those theoretical expressions for the sensitivity of the system's eigensolutions with respect to the inertia of the system, which can then be used to predict the change in the system response due to the renewable energy penetration and the magnitude of LLAs that can lead to those unsafe events. So to validate the theoretical analysis, of course, we consider benchmark systems, right, with various levels of renewable energy penetration at different buses and different locations of the system in order to mimic those low inertia conditions and then inject the different load altering attacks at different buses. And as you can see, the two curves that close much to each other in different kind of scenarios, right, are the ones from the simulation and the ones from the theoretical kind of analysis that shows a close mismatch that confirms the validity of the theoretical analysis to analyze load altering attacks under different levels of RES penetration. And the second thing that we have done is, as I mentioned, to analyze in the beginning, to analyze the impact of RES fluctuations during different times, and also the mismatch between the generation scheduling. So what you can see here is the first part is that high renewable energy penetration can increase the system vulnerability to load altering attacks. So essentially, the magnitude of LLAs required to cause unsafe frequency excursions is least when the penetration of renewable is high. This is shown between hours of midnight until 8 a.m. because this is from SPP RTO, which is in the Midwest in the US, which Southwest, which pretty much had a lot of wind renewable generation, during midnight until 8 a.m., right? And this is expected because the inertia of the system is least at those times, right? So you could essentially cause the same effect with a lower magnitude of load altering attack in the system. And on the right hand side, what you can see, we have varied pretty much the standard deviation of the forecast error of the generation scheduling. So a higher sigma in those kind of graphs essentially presents a higher mismatch between the schedule, conventional generation, and the residual load. So we can see pretty much here that the scheduling mismatch makes the system vulnerable as we increase it to load altering attacks, because pretty much this mismatch needs to be served by a fast ramping generator, okay, similar to load altering attacks. So the attacker needs to inject a smaller amount of LLAs in order to cause frequency deviations. So high renewable energy penetration, as we conclude here, with forecast uncertainty can further make the problem even worse. Why this is okay? So to address those issues from that we have developed, the second direction that we kind of work in my group is how to identify those attacks by identifying the dynamics of those conditions in local environments and what we call microgrids. So specifically, the research here aims to approach the problem locally by identifying residual dynamics of microgrid models to attack those attack conditions. And the focus is on the development of inverter-based modeling techniques to enhance these attack detection capabilities, right? And also a key aspect of this direction is also the emphasis on risk mitigation through defensive measures and control isolation techniques. So the idea of this direction is how to model via data-driven realization the system states of a microgrid environment. And in order to do that, we have devised in some recent works, small signal models for a cyber physical structure of a microgrid environment that incorporates local controllers, primary controllers for the inverter frequency, a microgrid centralized controller at the secondary at the low voltage of the substation, and for a more realistic characterization of the system model, we have also included process and measurement noises, modeling due to modeling approximations, model integration errors, and uncertainty. So the main idea here is shown in this graph. We have built what we call local detection schemes, communicate with a subset of interconnected agents in a distribution grid, in a microgrid environment. And the main idea is during real-time operation, each agent will utilize adaptive detection rates and estimation models of subsystem dynamics. So, and the main idea here is that the decision outcome for every local detection scheme to be transferred towards a high-level scheme that will not necessarily identify the event origin, but essentially mitigate the risk by disconnecting those distributed generation units that are vulnerable and preventing the propagation of the effect. And the detector here was constructed based on SKR, based stable kernel representation of the system in the attack-free case. And by collecting a large number of input-output measurements larger than the system states, we can build a sequence model from which this system matrix K, right, can be located in the subspace determined by the inputs and outputs. So by doing that, you can build an attack detector in a similar fashion in order to identify pretty much based on the knowledge of the input-output measurements to identify whether or not the system is deviating from the nominal condition. And following this kind of methodology, right, as I mentioned, the goal is to determine optimal isolation strategies in order to maintain grid stability by developing what we call supply adequate islands. So here the main idea is to develop pretty much grid optimization techniques considering load constraints, prioritizing critical load supply and minimizing the number of disconnected lines, generator constraints, ensuring operation within predefined limits, and then strategically segment the grid into stable islands, optimizing for minimal operational cost and maximum load serving. So following this formulation, this method pretty much identifies larger stable islands while avoiding uneconomical operation, line congestion, and load shedding. So before islanding, as you can see in this example, as well as after the islanding between two islands, right? And if you compare the cost, pretty much after the islanding, the aggregated cost is, of course, minimally higher, around 0.05%. However, both islands have sufficient generation and reserves to meet the current demands and any potential load increases after, an adverse attack in that location on bus number 4. However, in cases where contingencies may persist at that particular location, then the second island will be further segregated into another two. And since the system constraints will not allow the design of two stable islands, then essentially we have to prioritize the formation of a bigger healthy partition. So the one island here with blue color is able to supply the loads in the topology that is indicated. However, the second island with reddish kind of colors, we have to perform load shedding in order to continue the operation. And as you can see, 30% of the loads have to be shed in order due to the imbalance between generation and demands. And this also increases the overall cost by around 20-30%. And the most important thing here is that to make the islanding decisions quite fast, in that case, within 0.1 seconds, which is faster than the maximum threshold of 2 seconds that IEEE 1547 standard requirements mandates. Moving on to the third research direction, the main idea here is how we can ensure continuous and stable operation of power systems despite all those adverse events. And the main idea here is how we can develop models for resilient system operation or stability constraint system operation, which involves pretty much designing and implementing operational strategies that consider those worst case attack conditions. Security overall, right, is considered part of a larger resiliency architecture, right? So in power systems, the first step how to ensure grid resilience involves pretty much experimentation practices. For example, the use of digital twins, machine learning based models, Monte Carlo simulations, even hardware in the loop kind of testbed environments. And then the second is after the evaluation is enhancement practices that can be generally classified into planning-based strategies and that, for example, involved establishing grid expansion plans to harden transmission and distribution systems against events, and operational based strategies that the main idea here is to develop optimization techniques to utilize the available assets against those potential failures. So considering the second line of kind of category on optimization based kind of enhancement, resilient enhancement strategies, we have done some work that essentially the goal was to develop methods, right, that ensure system resilience despite, untrustworthy components in the system. The main idea here is how we can formulate what we call the state estimation problem of power systems in order to provide some probabilistic guarantees on the what we call the achievable level of detectability. The main idea in an essence is assuming a system that it has a lot of distributed devices that collect information back to the control center. And those devices either can be considered untrustworthy, so you don't want to include their data into your state estimator, or they provide falsified data. So the main idea here is how we can develop an algorithm or a method that based on the minimum number of channels, based on the minimum amount of information, can explain the observations that you see from the system in order to estimate the appropriate states, while at the same time having a high likelihood according to what we call an auxiliary model prior. So in order to do that, we have two phases. One is use historical data to train a data-driven model, and this model to generate a probabilistic estimate of the system observation as a function of this auxiliary data. And those auxiliary data, they have to be selected in a way that corroborates the underlying physical interconnection of the grid. And the goal of the online phase is to minimize the disparity between the observation and the system model, while at the same time satisfying these probabilistic requirements of the offline model. So in our framework, what we have used locational marginal prices of electricity, which essentially show the price of electricity at a particular location, right? And as we can see, they can follow pretty much physical quantities like bus voltages and bus angles. And we have used Gaussian process regression as a data-driven model in order to match those LMPs, locational marginal prices, to these physical quantities. And by doing that, we can see based on the figures here, as you can see on the bottom right figure. Let me make sure. On the bottom right figure is that we can have successful estimation results even when more than 50-60% of the sensors are failed, either because, again, you consider them untrustworthy or you cannot trust them, right? So there are more correctly estimated cases over state-of-the-art methods when up to 60% of measurement nodes are compromised, right? And the variance pretty much in the percentage of the state recovery depends pretty much on how prior information, right, affects the performance of the estimation scheme. And this estimation reduces the rates reduce with increasing bias, showing pretty much that the accuracy of the estimation scheme depends on the accuracy of the prior information. And in an essence, this approach shows promise because we can use readily available information to boost the secure operation of critical infrastructures against adversarial kind of attacks. In addition, some of the recent work here that we have done in this kind of theme is that we formulate what we call the optimal power flow problem in power systems for a small microgrid scheme, and then identify pretty much what is the worst case attack in the formulation of a bi-level optimization problem. So the idea here is operators, to ensure a stable operation of the system, they react by incorporating not only stability constraints but also the dynamics of the inverter models in those systems, as well as the design of a residual based detection observer. And by doing those conditions, you essentially can ensure stable and optimal operation of the system. So as you can see from the figures here, when the stability and network kind of constraints are employed during those attacks, the eigenvalues of the system move, further away from the imaginary axis on the left-hand side that provide a better stability margin. So, in summary, the 3D era of power systems, is here, right? There is a lot of diverse generation and load profiles with digital controls. However, still, the grid is exposed to many attack vectors. Unfortunately, there is poor equipment maintenance and the surrounding controls are not at the best kind of state. We don't have enough digital models, poor automation and monitoring kind of schemes. And unfortunately, because of the arbitrary installation of renewables in terms of location, sizing, and etc., as well as the passively operation of them, we still face issues. And this is why we need to develop what we call attack-aware and operational-aware approaches in order to secure cyber-physical systems. Just as let's call it an appendix, just to highlight some of the work we do here with some local Saudi industry. One important aspect is because of the high volatility of renewables and extreme weather variations that challenge the prediction of the grid behavior. It's very difficult in power systems, to do this enormous amount of simulations, right? And do an exhaustive analysis and synthesis to assess system resilience. So what we're doing, we're working to build what we call a robust stability assessment tool as a recommender system for grid operators that collects real-time data to analyze a grid, assess key stability indicators, and essentially support real-time decision making to ensure a stable and safe grid operation, while also considering the different kind of inverter controls, as well as the composition, as we say, of the generation mix. And the second thing that we are currently and in the last year heavily involved is what we call energy flexibility, pretty much on how to change generation or consumption patterns to support the electricity system, and essentially drive flexibility simulation by either direct or implicit load control, or a network tariff system, or a local flexibility market. So what we are doing, we're exploring demand flexibility, and formulate economic demand flexibility decision frameworks, considering distribution system operators, demand flexibility providers, and different kind of classes of customers to quantify their demand flexibility potential in distribution systems. And the goal is essentially integrate different network tariff systems along with load control and local electricity markets into a platform that builds upon forecasting, planning, and the operational status of the system to leverage the flexibility that is provided especially by large and energy intensive industrial loads. For example, desalination plants because of water scarcity here in the kingdom, as well as hydrogen electrolyzers, etc., etc. So, as the last slide, as I mentioned in the beginning, one aspect of the research that we do is that it's very important that those methodologies are being evaluated and conducted in realistic environments. And for that, most of the works that I presented and that we do in our group are being tested and verified in a real-time, testbed environment, in which we utilize the capabilities of both controller hardware in the loop, as well as what we call power hardware in the loop co-simulation capabilities for all the research efforts. So with that, I would like to thank everyone for listening. I will be happy to answer any questions, if any. Thank you.
Thank you, Dr. Harris, for a fascinating insight. And now we open up for questions, for folks can put their questions or ask questions. And I know we have a number of faculty also listening. So maybe I'll start with the first question. It's interesting. I liked what you said about, the attacker has to compromise a lot of sensors to manipulate a state vector, right? So you already have your auxiliary technique that you talk about has demonstrated some potential in it. I'm just curious about, you talked about this mostly load altering attacks, how do you distinguish, do you have any particular metrics that you're tracking for physical versus cyber that you see a clear delineation in between? How do we characterize, this physical and cyber? You talked about this attack aware and operation aware, but I'm just curious to see, are you looking at some specific metrics that distinguishes these two different things in physical and cyber in terms of this load alteration, right? Load alteration could be it could be due to operational, and sometimes there is a stealthiness, some kind of a real attack, or because you have so much of interconnected IoT sensors or in the network, right? And how do you juggle between these two decisions and see whether it's actually, is it physical or is it cyber? I just want to hear your
I
thoughts.
mean, that's a quite interesting question, right? I don't think there is, a straightforward answer in regards to that, right? Because as grid operation matters, at the end of the day, it has to have, a physical consequence to the system operation in terms of be able to disrupt the operation. Otherwise, it would be impossible, to be tracked, right? Of course, you may have other kind of stealthy attacks that focus more on energy markets for economic kind of consequences. But as far of LLAs, right, load altering attacks or or state estimation. The main idea is, you see a physical kind of consequence because of the implications of the attacker action into the system operation, and essentially, developing those themes or applications or methods that, despite potentially if this happens to the system, you ensure that overall the system will not be affected. However, how this can be detected, then there is different ways. For example, based on historical patterns, for example, in terms of load consumption. Fortunately, all the utilities around the globe, they have very good forecasting and prediction, for different kind of days, hours, events, etc. And also at the same time, you have also the capacity, for example, load altering attacks. It would not be realistic if all the load kinds of is aggregated and comes from a particular location because of the incapability of the system. So to do that, right? It will trip automatically. The main idea is um, controlling a large number of devices in a distributed way, right? And we used to discuss with some students the other day. One example is here at Chaos. As I mentioned, we're a small city, right? So everybody lives on campus. Houses here may have the same kind of, appliance in their house, right? A particular brand. So if an attacker, right, is able to exploit a particular vulnerability on those, high wattage appliances, for example, a washing machine, and be able to, or an air condition unit, and be able to change the temperature, the control temperature to 1 degree, and doing that in a mass scale, this will have a huge implication in terms of load change in the system that potentially may cause some events. So whether or not to distinguish between cyber and physical, it's a very difficult question, and it really depends on the particular threat model of the attack, as well as how that attack will propagate through the system, whether or not it's directly a physical attack, or a misleading, for example, information like the state estimation work, right? Misleading measurement information that will cause operators to mislead their further decisions. So it's quite tricky, quite difficult
Yeah.
to distinguish.
Thank you. I know that this is a pretty loaded question anyway. And I just want to ask your feedback, but thank you.
Yeah.
And we have other questions. I know we have a lot of power system faculty. Dr. Hussein, Jinlu, have any questions for the speaker that you want to ask?
Yes, one quick question. Uh, Very interesting presentation. Looking at your lab setup that you showed at the very end, I
Yes.
was wondering about you showed hardware for grid emulation or grid simulator, and then you showed Opal RT, Typhoon, and RTDS. Uh, For the Opal RT, or what do you use those three systems to do, and then you have the grid simulator. Can you simulate the grid on either one of those, Opal RT, Typhoon, or RTDS?
Yeah, great question, right? We're fortunately to have all these three kind of commercial simulators. Each one of them have different benefits and different drawbacks, right? For example, Typhoon is mostly focused with different and lower time scales for more power electronics type of simulations. Opal RT, I would say, is more universal for any type of real-time simulation. RTDS is more power system oriented. So and more an industry grade kind of power system simulation. Potentially, you can model in all of them, right? However, they have a few differences in terms of, for example, RTDS, you can develop a model, if I'm not mistaken, you can have part of the system different running in different time steps, whereas OPAL-RT cannot do that. On the other hand, OPAL-RT has this benefit, I'm not sure if you're aware, that integrates Exada CPS, a network simulator, and you can identify nodes in the power system in which are reflected in Exada CPS and do the network co-simulation with the power system. Whereas RTDS does not have this support, and you have to use, for example, NS3 and develop your own kind of integration system or some other kind of network emulator into that regard. So the development and the usability, it really depends on the particular needs, right? Not to advertise any of them in terms of what is best and what is not. Different, for example, projects that we had in the past require different kind of modeling capabilities, and this is essentially the underlying reason of having all of them in the lab. On the network emulation question, as you mentioned, OPAL-RT has this capability of do this power system network kind of co-simulation, as well as all of them can be. We have a work coming out on co-simulating different network real-time simulators, right? Typhoon with OPAL, OPAL with RTDS, and all the combinations to model different parts of the system in each one of them, because as you know, the capabilities of them can model a particular size of a system. So the combination of them using different protocols, for example, Aurora or sample values or analog inputs and outputs, can connect those simulators to model a larger system.
Okay. And the grid simulator, the Rigatron that you have, what do you use that for?
Those are what we call grid simulators. They are different than digital real-time simulators. The main idea of those is, for example, these real-time simulators can take, a low-level voltage and current signals, right? So if, for example, I have to draw power from the simulators back to the grid, I have to have a grid simulator that simulates physically the grid voltages and currents that connect to the real-time simulator, right? So if I have, for example, an inverter, right, connected to a solar PV or a remunerated solar PV, then DC output from that, from the output, the AC output from that inverter will be at levels that cannot be connected back to the real-time simulator, right? So think of them as the tools in order to exchange power with real-time simulators, and also draw power back from the real-time simulators, and they can also act as loads in the system.
Okay, very good. Thank you. I have other questions, but I think I give the time to others who may have questions. Thank you.
Thank you, Dr. Hussein. And Hussein and I was, also working on efforts to see how we can connect multiple RTDA or OPAL-RT systems across multiple institutions to do some co-simulation work. Would your system would be open for working with us to connect our test
Yeah.
bed with your test bed? And I think that's something we can learn. It looks like the funding is all provided from KAUST to get all these things. I'm just curious to see.
But cows industry, different
Okay.
funding agencies, we are all in the same kind of push for, but cows is generous, I must say. But in addition to that, we have some funding kind of projects, mainly through industry here in the kingdom.
Super, super. And yeah, and we have collections of, they have three ongoing DOE projects where we have built an NVIDIA's collections of at least 20 some NVIDIA devices, the AI test bed. We are working with different institutions to connect our AI test bed with different, power systems based co-simulation. So I think it'll be interesting to see how we could work with you on connecting our test bed. So we'll be in communications on
Happy.
that. Okay, let's see whether we have questions coming in. Okay, so how does your model distinguish between a malicious data injection and a legitimate grid event, such as extreme weather volatility that wasn't present in your historical training set for those rare events or any kind of?
I'm not sure for which part. I will try to give a quick and speculative answer based on what I understand, right? On the part of the state estimation, it really doesn't matter, right? What is the event, as long as you can consider the data untrustworthy or not available. On the load altering attack, I find it impossible because when you have an extreme weather volatility, I guess you are referring to the state estimation to wasn't present in the historical training set. The historical training set also I find it impossible because the data in that work was 5 year data from New York Independent System Operator that are public and available, the LMP prices. So pretty much you cover a wide range of different seasons and different years in order to capture them. And happy to chat more if you want, if you drop me an email.
Sure. Let's see. Okay, found the detection module integrated with the microgrid is really interesting. However, can you let me know if you use any DNN method or physics-aware methods for the detection module? And specifically, more on the adaptive detection rates, you mentioned in your using
Yeah.
agents, maybe it's only DNN or you have other partial Markovian process or some kind of reinforcement learning, or you using what kind of detection methods are you using?
In that work, we have used stable kernel representation in order to model an attack-free case, right? But in that particular question of Rafi here on the chat, right, we have not used any DNN kind of methods, but we recently had a work published with a collaborator from University of Cyprus on physics-informed neural networks for state estimation, right? And essentially, the main idea there is comparing those pins that a lot of people are working around the globe with different kind of ML type of methods, vanilla kind of deep learning methods, in order to compare how well do they behave in case of data manipulation attacks. And the main idea there is that, again, without having a lot of data, because you have bet the power flow equations into the loss function of the problem, you can have, in most cases, better kind of accuracy than any other kind of pure data driven technique. This is a paper that was published maybe last month. It's called Physics Inform Robust State Estimation Using Physics Informed Neural Networks, if I'm not mistaken, the correct title.
Sure. Okay. Thank you. Any other final question? We almost ran out of time. Any one final last question anybody wants to ask?
So
Uh,
maybe ask one last question. In
yes, Dr.
general,
John.
what is the different how what is the basic the metric that you will use to distinguish between a system the power grid failure and a cyber attack? What is the major criterion to be used for differentiating between these two different two items?
Again, difficult question. If I want to answer simply, is the spatial temporal correlations and the spatial temporal analysis that exist in a grid network, right? Just to give a simple example, right? In a power system, if you have a normal fault condition or a fault in the system, which is a normal behavior, right? You can exhibit some deviations in terms of voltage, frequency, etc. Not only in that particular location where is the grid, but also in all other measurements, in all other occasions, in some degree, right? In terms of spatial, but also in terms of time, in terms of temporal analysis, right? The main idea of differentiation between cyber attacks is what we call them or abnormal or not behaving or not following physics or equations or in form kind of operational principles of the system. So this is in a high level the main differentiation, and then based on a particular study, threat model analysis, etc., you can use different metrics, right, in order to do your system analysis. But in brief, the main idea is the spatial and temporal analysis that normal grid phenomena essentially will have as part of the different algorithms that you're gonna implement or have built in within power system operations.
I see. Thank you. And so basically, you said that you're trying to identify two different kind of the footprint leading caused by different. But sometimes I'm also kind of curious about for some smartly made of the attack, it may just attack us to the right place to make the footprint to be somehow looks like just like a natural disaster, okay, or natural failure in the power system. Yeah, I know that should be a difficult problem, and I just want to follow up to see anybody has done the more detailed analysis on that. Okay.
Yeah, I mean, this is very interesting question, right? And I think we're leading there, right? It's a cat and mouse game, right? Well, everybody working in cybersecurity know that, right? It's one step ahead. Always attackers one step ahead. Try to catch the next thing of developments, right? It's not an easy task. And of course, right, by embedding different kind of modules, let's say, in the system, you try to capture those abnormal patterns that may exist. Of course, this is not an easy task, but yeah, I think on the other hand, all these attacks happening kind of reveal also the trend of what is going on, and what you are saying is spot on, right? Trying to emulate system behavior that can seem nominal to the system is the right way in order to not fully distinguish whether it's an attack or not.
Super. Thank you, Dr. Harris, I think, and Dr. John for the question. So in the interest of time, we're going to wrap the webinar. I appreciate Dr. Harris for your time this morning with us, and you will receive a nice plaque from UND, and look forward to working with you and, getting to know more and see how we can collaborate. I appreciate for you being here with us, and thank you so much.
My pleasure. My pleasure. Thank you for the invitation. Take care.
Take care. Thanks.
Bye-bye.